South pole. Okay, let's pretend that that's not a bunch of circles that I've turned sideways, that it actually is loops of a coil, and that the current is going up the front of the coil. Well, if it's going up the front of the coil, the north pole is this side, yeah? Wrap your fingers the way the current, so up the front, down the back, yeah? So it's a coil. I'm trying to draw something like this, only with wire wrapped around it. I meant to have a coil up here, but I didn't. Okay? So we wrap our fingers. If the current's going this way, this is the north pole. How many people made little magnets when you were like younger with batteries and yeah? And you always, it's like, well, you probably never worried about which one was the north pole. I didn't either. I wasn't that smart, but you know, there it is. Pass that back. All right. How about this one? Current's going to the right on the front of the coil. So it must be going this way, right? Which way is our north pole? Straight up, the top side's the north pole. Let's see. It's going down on the front of the coil. Yeah? Get your hand out. Everybody get your hand out. No calculator, just a hand. This side must be the north pole, right? And then how about this one? Let's see. Wrap your fingers around. North pole must be down. Yeah? It's the end of that show. Yeah. It's up to you, yeah. It's always up to you. Okay, this is the formula. This is our formula for force on a current carrying wire. Force, and they say they do this the wrong way in the data packet, but this is ILB sine theta. Okay? Now, it really is, when you get to grown-up physics, they're really going to say that it's IL cross B. Right? IL cross B is a vector cross product. Okay? It has a particular direction. It's the most bizarre mathematical relationship, but this happens a lot in physics. Okay? And what it means is that it is this force, ILB sine theta, where theta is the angle between the current and the magnetic field, right? And then it is in the right-hand direction. Right? It's in the right-hand direction. And the right-hand direction, by the way, is perpendicular to both IL and B, right? And this is kind of fun. Once you get the hang of it, you can predict things that maybe nobody else cares to predict. But they can't predict it. You can do it. I'm afraid I am telling you how effing magnets work. All right. Twixt. That's what you write when you're too lazy to write between. So what this means is, if we've got a magnetic field, okay, to the right on a page, and then we've got a wire right? And the wire intersects the magnetic field for some length L. Right? So basically L is the amount that the wire and the magnetic field overlap. Yeah? The magnetic field might be bigger than the wire, it might be smaller than the wire in this case, right? Okay, but that's that, right? Okay, and then the angle, by the way, in between the magnetic field, this is our magnetic field here, is that angle right there. And of course 90 degrees gives you the biggest force, right? All the way down to if we actually made the wire parallel to the magnetic field, there would be no force, is the way the formula works, right? Okay, but right now that angle is 90 degrees. Okay, and then let's give the current a direction. Okay, here's how you figure out the direction of the force. Here's how you figure out the direction of the force. Take your index finger, this is our right hand rule, okay? The third one is I cross B. This is a cross product. Okay? What you do is you take your right hand and you go like this. Now the book shows you how to do it, and this is what I learned was like this, right? It's like, anyway, with the hand. So if you read the book, it's got like something with the hand. I'm going to show you something that I learned from a kid from Hong Kong, right? Because I was showing kids all this stuff, right? Which requires like gross body movement, right? Kind of wears you out. And he was just like doing this thing with his hand like this. I'm like, that's slicker. Okay, so I'm going to teach you that way to do it, right? What you do is you make your hand first like this. Your thumb is at right angles to your index finger, which is pointed straight out, and your middle finger is pointing straight down, if you can do that, right? Okay? Now, what you do is you do this so that with your right hand, right, your index finger is like the current and the length, right? The middle finger, your middle finger is the magnetic field, and the force is your thumb. Okay? Your magnet is the thumb. So let's look at this example right here. Okay? We got our index finger up the page, yes? Magnetic field is that way. Yeah? Which way is your thumb pointing? That way. So this wire would actually be moving away from us, right? The force would be into the page. Now, we're going to do enough of these problems that we have to be able to signify up the page, to the right, down, etc. But we also have to be able to say into the page and out of the page, right? And so the convention in physics is this, okay? A dot is out of the page, right? This is like the last thing Custer saw, right? Is the tip of the arrow coming toward him, right? Whack, right? When he finally took on the Lakota warriors instead of killing their women and children, right? This is what he got. Okay, I taught it in Indian school, so I might have a biased reflection of history, right? And then I know that arrows are not four-fletched. Four-fletched arrows don't fly straight, but X means into the page. Isn't that weird? Fletchings on arrows, there's always 3 feathers, right? There's never 4. Anybody ever make a 4-fletched arrow? They're fun. You never know where they're going to go. It's like, where is it going to go? Right? Don't use but you know, the 3 ones work pretty well, right? So into the page, you're seeing the feathers. It's like an X, right? You see the feathers, and then if it's coming out of the page, you see the point of it, right? So we would say that this force, on this one, we'd say force is into the page, right? Or we could say it's an X, right? If we want to just use a symbol. It's into the page. X means into the page. Okay. So now we've got this thing here. Is the north on this side?
Oh, I see.
Is the south on the bottom side? So this is actually a fairly hard problem for this, right? Okay, so if the north is on the top and the south is on the bottom, let's draw a little picture. If the north is on the top and the south is on the bottom, which way is the magnetic field? Concept 0. From north to south, yes? The magnetic field is from north to south. So concept 0, we've got to know, given a configuration of magnets, which way the magnetic field is, yes? Okay, now, is our current's going the wrong way, isn't it?
Yes.
Okay, that's bad. But anyway, we can we'll just ignore that one. Let's do this one. Okay, if the current is this way, everybody point that way. Yeah? And the magnetic field is which way? North to south. Which way should the force be? It's toward me, correct? Away from you, toward me. Watch. I'm going to turn on the current. Watch which way that wire goes.
Oh, Jesus.
That's crazy.
Jesus.
Now let's reverse the direction of the current. So it's now going opposite the direction of the arrow. Okay, let's do